Good afternoon, ladies and gentlemen. My name's Greg Taylor, but I take no part in these proceedings other than to carry out an introduction of Professor Mario Wüthrich. Mario's here with the help of funding provided by the Institute, an Institute research grant, which has assisted in bringing him here for the month of May to study general forms of dependency in chain ladder structures in conjunction with three researchers at UNSW, Benjamin Irvanzi, Bernard Wong and myself. This coordinates very well with an Australian Research Council project which the same three researchers are conducting under the rather lengthy title of Modelling Claim Dependencies for the General Insurance Industry with Economic Capital in View. And that research project conducted in collaboration with three major Australian insurers. Coming back to Mario, he's internationally well known and highly respected as a researcher in the field of loss reserving. He's well known for his 2008 book with Michael Merz on stochastic claims reserving methods in insurance. He's perhaps done more than any other researcher to endow the chain ladder with respectability. Mario is professor in the Department of Mathematics at ETH, or as we would call it, ETH in Zurich, and some of you may recognise that as one of Einstein's universities. He's Swiss Finance Institute Professor, Honorary Visiting Professor at City University London, and Honorary Professor at University College London. He holds a PhD in Mathematics from ETH and is fully qualified as an actuary with the Swiss Association of Actuaries. From 2000 to 2005, he held an actuarial position at Winterthur Insurance in Switzerland. He was responsible for loss reserving and developing and implementing the Swiss Solvency Test. He's a member of the board of the Swiss Association of Actuaries, editor of Aston Bulletin, and associate editor of the European Actuarial Journal. He's written a number of research papers, a largest number, and several books. I already mentioned the 2008 book, but in addition to that, Market Consistent Actuarial Valuation in 2010 and Financial Modelling, Actuarial Valuation and Solvency in Insurance in 2013. Please join me in welcoming Professor Mario Wüthrich.
So, first of all, I would like to welcome everybody. I would like to thank Greg for this very nice introduction. But not only this, I think it's only thanks to him that I'm here today. But moreover, I mean, in 2000, when I started to work in the industry, this was exactly the time when Greg's new book, or Greg's book, was appearing. So I started as an actuary in 2000, and probably my first task at Winterthur Insurance was to give a seminar on Greg's book. So he kept me busy for at least 6 months, because in this weekly seminar I had to present, I was forced to, chapter by chapter of his book, and I think this was probably one of the best introductions, and also based on these presentations, I started to teach a whole lecture on claims reserving at ETH from 2006 on. So I would like to thank you. I think you have strongly influenced me, but also my research. And the thing I'm going to present today, that's based on the chain ladder method I would say that maybe half of the slides are not really new, or the contents is not really new, because I'm going to just explain once more the whole chain ladder model. And then in the second part, I'm going to explain how we use these ideas to get more insight in what is going on in this triangle. So the second part of the talk is, I would say, completely new. That's a paper that we haven't published, but we have put online in 2014. And at the same time, we have also, so I have jointly with Markus Gessmann, who is responsible for the R-package chain ladder, I have also collaborated with Markus, and the whole thing that I'm going to present today is already implemented in the R-package that you can download, so the one that is called chain ladder, that you can download, and you can easily use these formulas. So you don't have to code them yourself. It's already done. Okay, so let me start. Maybe can, yes, it's even better. So, as mentioned, I would like to give you some introduction, and this will mainly, once more, explain why this field is so important. I will rediscuss the chain ladder model, and when I speak about chain ladder model, I always mean the Mach model, so it's not, I usually don't speak about the Orbis-Pittsburgh-Poisson model when I speak about chain ladder. Then I would like to discuss the claims development result, which is maybe less familiar in Australia because you have slightly different solvency rules, but this is at the heart of research at the moment in Europe, because that's what you have to do for Solvency II, but also for the Swiss Solvency Test. And finally, I would like to complete the picture by giving examples, by showing you why this is useful, but also important. So let me start with the balance sheet of the company I have been working for. So this company, that's the biggest one in Switzerland, and it has about 14 billion, actually Swiss francs, or almost like Australian dollars. It's slightly more. So they have almost 14 billions of assets, and you can see how they invest their assets. So these are the assets, and at the same time, on the liability side, you can see that by far the largest position are the claims reserves, which are more than half of the total assets. Then there are some more reserves or provisions. These are for annuity payments, mainly in accident insurance and motor third-party liability insurance. Then they have some other liabilities, which is also quite a huge position. There are some more things, and then you can see that it seems to be quite a wealthy company because they have free capital of about 2 billion. But you should also note that this 2 billion is before paying dividends, so this will still decrease once they pay dividends. But what you should note is that the claims reserves are by far the biggest position in the balance sheet. And what one should also know is that this position, that's a pure prediction. It somehow tries to predict, as I will just show, and to value the liabilities that you have collected in the past and which you still need to pay in the future. And we all know that we would like to be better in predicting things, so usually we are not so good in doing predictions. I mean, you can already see that if you are only wrong by 1%, it's a huge amount. And at that time, I was working for this company from 2000 to 2005. We were exactly 5 people in the whole company who were responsible for this number here. 5 people. So everyone, so we were sharing 7 billions. Also sometimes during nights when we could not really sleep because we didn't know what to do. So let me briefly, but I'm sure you're all familiar with this, briefly just explain why these are predictions. So let us assume that we only write contracts which have a 1 year period, term period. So typically for such contracts at the beginning of the insurance period you collect a premium, and then with this premium you take over all the claims or the financial part of the accidents of claims which have accident, let's say accident date somewhere within this insurance period. And now the difficulty is that typically you cannot immediately settle the accident on occurrence. So first of all, there is a reporting delay, because typically people, they do not call, let's say, the company immediately, but there are also other examples. So in our company we had asbestos claims, and these are still court cases today. So the company doesn't know, first of all, reporting usually comes very late because the disease, the outbreak of the disease is much later than the accident. So this can be, for those particular claims, this is typically between, let's say, 10 and 20 years. So there is a delay on the one hand in reporting, and once it is reported, then you have this claim in your statistical database, but still typically you don't know all the details, you don't know how much you will need to pay for this claim. So there is another delay, which we call the settlement delay, and during this settlement delay, which can also be days, weeks, or even years, you do several payments until at some time point you can finally assess the claim where you know how much you have to pay for these claims. And also here, I mean, there are several reasons. A very simple one, legal reason in Switzerland, is that claims where childs are involved, disabled, you can only settle them once they're 18. So if the accident happens when this kid is 5, then for sure the settlement delay will be at least 13 years. That's for legal reasons. But there are many, many other reasons which also cause these delays. So what we need to do is let's say if we are here on the time axis, so what we need to do is we need to predict what we still need to pay for all these claims which have occurred in the past. And this prediction, or you could also do evaluation, this prediction and evaluation, that's exactly what you need to put into your balance sheet. And of course, this amount should be, on the one hand, sufficient to pay all your obligations, but on the other hand, it should also not be too high, because, I mean, you also have to pay dividends to shareholders. And moreover, this prediction should be, let's say, as good as possible, because if you don't know how much your old claims are costing, you for sure will also not know how much you will need to charge for new contracts. So that's why you really need to have good predictions for future payments of claims which have occurred in the past. So the notation, I would say that's quite standard. If you work on triangles, then what you typically do is you have accident years. So that's when the claim occurs. You have accident years on the Y or on the vertical axis. So let's say we have accidents which have occurred in 2009. So these are accidents which belong to contracts which were signed for year 2009. And on the horizontal line, or on the x-axis, you have the development delay. So for these 2009 claims, we pay 1,000 or 1 million or whatever. We pay 1,000 in 2009 itself. We have paid, if this is already the total, we have paid 1,200 after 1 year of delay. We have paid 1,000, roughly 700 with 2 years of delay, and so on. So what I do is I denote these cumulative payments where I do not discount, so these are nominal cumulative cash flows, by Cij, where I is always the accident year and j is always the development year. And in the upper triangle, so that's where I plus j is less or equal to today's time point, let's say 2013, so where I plus j is less or equal to 2013, which is the upper triangle. These are our observations. And what we need to do is we need to predict this lower triangle, because this will exactly tell you how much you still need to pay for claims which have occurred before 2014, but for which you still have some open liabilities which you need to pay somewhere after 2013. So I call this Cij, and the data at time t is typically called or denoted by dt. Now, the chain ladder method, which is probably one of the oldest methods in non-life or general insurance, somehow is based on the idea, and that's why you structure the data like this, that if we consider all the payments, let's say, of a fixed accident year, which are done after development period j plus 1, then this is roughly proportional to the previous one, meaning that you just need to consider the previous one and multiply this with this proportionality factor. So for instance, if you consider here the third column, so this third column is more, or should, if this model applies, should more or less be proportional to this column, the previous one, which means just multiply, let's say, this 1,700 with this proportionality factor, and then you should roughly get this 1,971. And you can see here, and that's not a coincidence, that if you consider, let's say, the red column, that's more or less twice the first column, which means that this rule more or less applies. I mean, by the way, that's simply linear regression, where we somehow forget the intercept. Oops. And now, of course, what we need to do is we need to somehow find out if this is the right model, what these proportionality factors should be in order to complete the lower triangle. And that's exactly the idea of the chain ladder method. And based on this law, Mach, he tried to design a stochastic model which follows these rules. And so what he assumed is the following in his 1993 paper, that there are fixed constants which are his proportionality factors, and then there are some variance parameters, such that if we look at one row, that these rows are independent, so accident years are independent, meaning the development, let's say, of 2004 claims are independent of the development of 2005 claims, and as a function of the development delay, they should be Markov processes, meaning that if you want to predict the value tomorrow, you don't need to know the whole history. It is sufficient to know where you are today, and the knowledge where you are today completely determines what is going to happen tomorrow. So we don't need to record the whole history. The state today is already sufficient to know what is going on, or to do a good prediction what is going on in the future. And then he made the following assumption, that tomorrow's payout, cumulative payout in average, if we know where we are today, is exactly the value today multiplied by this positive constant called the chain ladder factor. And then there is a variance assumption, and for a moment I don't want to comment further on that, but we also need some second moment in order to derive for some framework where we can quantify the quality of our predictions. But you can see, I think, the crucial assumption, that's the first line, that this exactly has the property that tomorrow's payout in average or is more or less proportional to today's payout. And then what you can do is so I say that we would like to complete a lower triangle, which means you somehow want to derive the last column, because once you know the last column, you know all your liabilities. And under these model assumptions of Mach, you can now easily calculate the value in the last column based on the upper triangle, on today's observation. So if you apply all these properties, what you will find is that you just need to consider the last value on the diagonal or the last observed value for this accident year. And this needs to be multiplied with all these chain ladder factors which map this value to the last column. So that's how the lower triangle or the last column of the lower triangle can be completed. That's what you would do if you would know these proportionality constants. But the difficulty is that you don't know them. Typically, you don't know them, so you need to estimate them. And you estimate them by this formula. I'm just going to explain on the next slide. So you're going to estimate them based on the observations in the upper triangle, and then what you do is you replace these unknown parameters by the estimates, and then you get a predictor for the last column, which now can be fully calculated once you have the observations in the upper triangle. And just two remarks, or one remark is that this estimator has lots of good properties. So first of all, they are uncorrelated. So this one from the next one is uncorrelated. And the second good property is that they're unbiased for the true values, which means that if they're uncorrelated and unbiased, that also the product is unbiased, which means that this is an unbiased estimator for this conditional expectation, which we don't know. And being unbiased, that's typically a good property, because then you know, at least in the average, you do the right thing. So let me explain how you calculate this. So the way how you calculate this is simply you calculate the column sum, let's say, of development delay 3. You divide it by the sum of exactly the same cells, but one period before, and since they are proportional, if you divide this by this sum, that's exactly what we do here. We divide column 3 by column 2, then you get this estimator which is 1.1981 to map column 2 to column 3. So that's how you estimate these chain ladder factors, and then just take the last value on the diagonal, let's say this one, multiply this one with your estimate, you get the next one, and then multiply again with this estimate, and that's how you map or how you project this last diagonal to the last column. And that's what you do, and that's how you calculate the reserves that we have seen in your balance sheet. And now, and that's why we need the stochastic model, now, of course, the main question is, if that's now a prediction, what is the possible, so that's our prediction here, what is a possible deviation of the true payout compared to what we predict? So what we would like to do is we would like to have a measure for the quality of our prediction. And that's why we need the stochastic model. I mean, up to here, completing the table, that's what has been done for, let's say, the last 100 years. For this, you don't need a stochastic model. But as soon as you want to assess prediction quality, you need a stochastic model which somehow allows you to derive confidence bounds for your predictors. And that's exactly what we would like to do. And probably the easiest risk measure is the variance, or the L2 measure. So what we try to do is we try to assess the L2 distance between the true payout and our predictor. And we would like to do this conditional on exactly our upper triangle. So we would like to do this conditional exactly on our company. I mean, if you have different companies, you may want to average over different triangles, but if you are working within one company, you want to have this conditional L2 error, because that's exactly the prediction uncertainty that you face within your company. So what we try to do is we try to assess this mean square error of prediction, and that's exactly the main achievement which has been done in this 1993 paper of Mack. By the way, I was told that this is the second most cited paper in the actuarial literature, but I don't know which one is the most cited one. But for sure, this shows that this is one of the most important papers. So the formula derived by Thomas Mack has this form, and you should not try to understand it right now, because I'm going to give the interpretation only later. The only thing that you should note is that what he did, he gives an estimate for this mean square error of prediction, or the conditional mean square error of prediction. And this is an estimate because of two reasons. First of all, we have seen that we have parameters we don't know, so we need to estimate them. So you can see that there are estimates for parameters, so that's why this is an estimate. And secondly, there is a second term which we call the estimation error, which is somehow on top, and also this cannot be explicitly calculated, and Mack gave a way how you can tackle the problem of somehow giving a number what the possible estimation error could be. So for these two reasons, this is an estimate, and that's the formula that is usually used in order to assess prediction uncertainty in a chain ladder model. That's for one single accident year. If you do aggregation over accident years, the formula looks slightly more involved, but this can also be derived. And if you do this, so first of all, that's our predictor. That's what we have paid, so we get our reserves. So in the example I have shown before, we have reserves of, let's say, 10,000. The standard deviation, or the square rooted mean square error of prediction, is in this example 1,500, which gives you a coefficient of variation of 15%. And you can see that in our previous, in the balance sheet, if this 7 billion would have an uncertainty level of 15%, then we would really be in trouble. So this is what has been done, let's say up to 2007, 2008. And in 2005, or let's say 2003, the European insurance industry was hit by a crisis, and people started to develop these new solvency rules, and I mean, we soon realized that the Mack formula is nice, but in order to assess uncertainty, let's say for accounting, it's not the right time horizon. The Mack formula studies the uncertainty. So the Mack formula, it assesses the prediction uncertainty over the whole lower triangle, so over the whole entire runoff, which can be viewed as a static view. But when you do solvency, you do this on a regular basis, which means that you somehow need to get away from the static view to a more dynamic view. And that's exactly what we try to do for solvency considerations. We try to somehow change the Mack formula into something which is more dynamic, meaning that if I predict today my total claim, let's say by Cij today, meaning at time t, by this value, then what I do is I collect information over the whole year, and at the end of the year, I will update my prediction. And updating my prediction means that I get a new predictor at the end of the year, which means that based on this new information, the 7.1 billion, maybe in 1 year,
I will say it's not 7.1, but it should be 7.3. And this difference between these two predictors, that's exactly a claims development result. And the claims development result is exactly the amount, if it's negative that, or positive, that has to run through your earnings statement. So if I go up from 7.1 billion to 7.3 billion, I have a loss of 200 million, and I need to finance this. And that's exactly what Solvency tries to do. It tries to see the dynamics of this process, and if this is too volatile, or if it's volatile, you need to hold a lot of risk capital in order to finance within the next year possible fluctuations of your prediction updates. And that's exactly the claims development result. And of course, what you will do is you do your prediction today as good as possible, meaning that, and tomorrow as well, meaning that today's prediction is in average right for tomorrow, which means that in your earnings statements, in average, if you have to do a budget for next year, in average, you will predict this position that you will have a 0, because if you do a good job, then tomorrow's predictions should somehow fluctuate around today's prediction, which means in average, the claims development result, which you can only observe at the end of the year, should be 0, which means that this should be exactly balanced tomorrow's prediction around today's prediction based on today's information. And what we need to do now, so that's today's prediction. You collect the new information next year, and based on the upper triangle now, including the star information, you do this year, this new prediction. And in order to now assess the uncertainty in your earnings statements, what you need to do is you need to see how much the claims development result, which is exactly this fluctuation, deviates from your prediction that you do. And that's exactly what we call the one-year uncertainty, or the claims development result, the mean square error prediction of the claims development result, because it exactly assesses the volatility that you are facing in your earnings statement within the next year that is coming from the loss reserves that you are already holding in the beginning of the year. So that's the formula which gives a more dynamic view, at least over the next year. And that's exactly what we did in order to change the MAC formula to get to the more dynamic solvency view, which tries to assess uncertainty within the next year and not within the whole triangle. So that's what we did. That's the formula which is now used these days in Solvency II and the Swiss Solvency Test. It has this complicated structure. That's what we did in 2008, but there are at least, let's say, 6, 7 other people that have also done the same formula, but we were the only one who have somehow published the formula. I mean, our Italian colleagues Morricone, De Felice and Morricone did it for the Italian regulator. There were people working for the German regulator. And then it was Peter England, he did it in the UK. We did it for the Swiss regulator. So it's not really our formula. They all had the same formula. And nicely, in September 2014, there is an industrial discussion paper by Eric Dalmoro. I think he's the scientific chair of ASTIN these days. And Joseph Lowe of Aspen, UK, they said that the problem is basically solved in the chain ladder method. So it seems that everyone is happy. But this was not really the case, because I think everything was here and people realized that everything is here, but I constantly got emails of people asking things about this formula. And in the beginning, you like these emails because you see that people use your things that you develop. But at some point, it gets a bit annoying because you don't want to answer the same questions all the time. And that's when Michael Merz, and that's Michael Merz and I decided to write a more, let's say, pedagogical paper, which somehow just tries to re-explain the formula. And we did something very unusual. In actuarial literature, we have started to use colors. And now let me explain the formula. So this is the total uncertainty formula of Thomas Mack. And basically it has two terms. There is the blue term and there is the red term. The blue term, this is called the process uncertainty. I mean, that's the uncertainty you cannot really get rid of, because what you try to do is you try to predict random outcomes, and since they're random, they will fluctuate somehow. And there is just a natural uncertainty within your model, which is explained by this process or variance, process uncertainty or variance. And then there is a second term, which is the red term, and this is exactly the term which is called the parameter estimation uncertainty, because we don't know the true chain ladder factors. We need to estimate them, and typically you do some errors in estimation, or also there you have some kind of fluctuation. And the second term, that's exactly the term which comes from, let's say, parameter estimation uncertainty, or you can also call this model uncertainty, if you assume that the chain ladder model is the right model, but still you have some parameters which you need to estimate. And that's what you are facing over the whole lower triangle, or for a given accident year, over the whole future development, which means that over all future development periods after the diagonal you have observed, so that you sum this over all j's. Now the 1 year formula, our formula, has now the following form, and this should now be compared to the total uncertainty formula. So the first observation is that from the process uncertainty, you exactly collect from this whole sum, you exactly pick up the first term. So for the 1 year uncertainty, only the first term survives from the process uncertainty. And that's not a surprise. For the parameter estimation error term, also exactly the first term survives. Okay? Because, let me just go back. After 1 year, you have observed this value here, which means that all the uncertainty which are related to this red star should disappear. And that's exactly the meaning of these two terms. But then there is something else which still appears. Now, what is the interpretation of this term? So first of all, you can see, the first term we got rid of, so that's why the sum now starts one index later. And then we have exactly these terms here, but they are multiplied with an alpha, and this alpha, that's a number which is between 0 and 1. Okay? Now the interpretation of this alpha is that this can be viewed as some kind of credibility factor. Now, if you collect this new information, then you can also improve quality of parameter estimation. And this here is exactly the improvement of parameter estimation error, the improvement of your parameter error when you have a new information, and that's exactly the proportion by which this uncertainty is reduced. Okay? So that's interpretation of these three terms: process uncertainty, which disappears, and parameter uncertainty, which disappears for the next cell. And for all the remaining cells, there is a reduction in parameter error because you have more information, which allows you to give better estimates for the parameters. So that's how we explained the formula in this paper, 2014 paper, which you can download. But colors are really helpful, because only at that point I realized that you can now pull this machinery forward. I said this is the prediction uncertainty for the next year. But if you really understand these colors, you can immediately make a guess what the prediction uncertainty will be for the accounting year in 2 years, or in 3 years, or in 5 years. Just look at the colors. So these two terms disappear. So I guess for the year after, what you should do is the following. You should have process uncertainty in 2 periods. Then the parameter uncertainty in 2 periods should disappear, but it was already reduced by alpha in next period, so it only remains 1 minus alpha. So that's parameter uncertainty in 2 years. And then you collect the new information. New information will reduce parameter uncertainty for the whole runoff. So that's if you understand the colors, that's the immediate guess what should happen in 2 years from today. That's what we realized when we saw these colors, and then you start to prove these things and you find out that they're almost correct. If you do this, this is exactly the first term of the Taylor expansion, and there are higher order terms, but similar to the Mach model, or the Mach method. In the Mach method, there are also higher order terms, but typically they are negligible. Also here there are higher order terms, and all the higher order terms are negligible, which means that this is the leading term of the uncertainty in the accounting year in 2 years. And now very nicely you can drag this forward. So for the year after, you have again the blue term, you have a red term which will be 1 minus alpha to a square, and then how you reduce parameter uncertainty. And this now explains how the Mach formula can be allocated to the different accounting years. Because if you then sum up all these individual uncertainties, the sum is exactly the Mach formula. So this explains, when you have the uncertainty formula over the whole runoff, how you need to split uncertainty across all future accounting periods. Now this looks terrible, and I'm going to give you some remarks later on. But let me now give you some examples. Let me start. That's a US motor third-party liability portfolio. So this is always normalized to 100%. So we estimate or we predict the payouts, which gives our reserves. And then with the reserves and the chain ladder pattern, you also get a cash flow pattern, how these reserves are expected to be paid out over time. So for instance, so that's exactly the blue line. So for instance, for this MTPL portfolio, US portfolio, so what they do is they can release or pay out roughly 60% of the reserves next accounting year. Then they pay an additional 20% in 2 years, an additional, let's say, 10% in 3 years. So the blue pattern is exactly the expected runoff of the reserves. Okay? And now using the splitting formula of the Mach total uncertainty formula, you can do exactly the same for your uncertainty. If we call uncertainty this mean square error of prediction uncertainty, so you can now exactly track, if you believe into this model, how uncertainty is released. And there is a very typical picture, so the release of uncertainty, that's the red figure here. Very typically, the red line is always above the blue line, which means that a release of uncertainty typically is much slower than the release of reserves. So for instance, here you pay out 60%, but the uncertainty is only released by 40%. So if you use reserves for scaling uncertainty, I mean, we all know this, if you use first moments to predict second moments, that's a bad thing. And that's exactly what you can see here. So typically, uncertainty remains in your portfolio much longer than the reserves. And the reason, I think, is clear, because what you do is typically you first settle the small, simple claims. You do lots of payments, small payments, you get rid of lots of reserves. But these lots of small claims, these are not really the claims which trigger uncertainty, which means you have lots of payouts, but the complicated claims you still have in your portfolio, because they're only settled around here. So that's the US motor portfolio, and US business seems to have a rather fast runoff. I don't know why, but it's like this. The Swiss portfolio, as I said, if you hit a child, you have to wait at least 13 years if this is 5 years old. And you can see that motor insurance in Switzerland has a very slow runoff. I guess it starts 2014. And basically the reserves are paid within 16 years. Everything is settled. But you can see that the release of uncertainty is much slower. By the way, I have always been speaking about Solvency II and this one-year view. But, your prudent reserves is, what is it, the 70% quantile? Or is it the 60? I don't know. 75. So, if you assess the 75% quantile just using somehow a standard deviation formula, then the splitting formula exactly tells you how you need to assess this margin to the different periods. Okay? So if you have a margin of 200 million, then our formula tells you need the first 20 in the first year, the second 30 for the next year. So this exactly gives you the runoff pattern of this security margin. So what you should also observe is that, that's what we have been discussing in Europe, that this substantially depends on legal environment. So there is not a European pattern. Every country has to do this themselves. Then it's hugely dependent on business lines. So here there is a commercial property insurance portfolio of Switzerland where you pay 80% in the first year and you release about 60% of risk in the first year, and that's settled after 5 years. There is a general liability portfolio where, again, we have a much slower runoff, but as always, almost always, red is above blue. I only have 2 or 3 examples where it is the other way around, but that's social insurance, which is run by the government, and I don't know what they are doing, but there is something wrong in the data, I guess. But then there are also very special products like collective health insurance in Switzerland or building engineering in Switzerland. So, for instance, collective health insurance, these are salary payments for employees which get sick. But once you get sick, you get a salary for at most 2 years, and after 2 years, you have to move into the social security system. And you can see this exactly here, that after 2 years, everything is settled, and you still expect money to come back, because typically you pay too much, and then you get some things back from the company. Also in building engineering, that's typically after 2 years, you have paid 20% too much for the claims, and then there are some back payments by constructors over the next 5 years. So the blue thing is how you pay out your reserves, but you can see that there is huge uncertainty how these payouts will come back. Now, especially these 2 businesses are strongly dependent on the economic environment. So this is essentially triggered by bankruptcy of constructing companies. And if financial markets go badly, then you will not get your payments back, and in addition, you have to pay much more, and that's exactly what is reflected by the runoff of risk pattern. And you can see, I mean, there is no way how you use the blue pattern in order to scale risk over time. So you really need the splitting formula. So what you can find in the paper is that we split we generalize the 1 year formula to any accounting year, and what has been gained is that the total uncertainty formula can now split across different accounting years. So this explains how the runoff of your risk is. By the way, the first time I presented this was at the biggest Italian insurer, and this was quite funny because they had a big round table on the right-hand side where all the actuaries. They are working in Milano, and on the left-hand side there were all the risk managers who are working in Bologna. And when I was presenting this, they were all smiling, and I said, wow, now we have much better understanding of risk. And then on the risk management side, suddenly someone said, but if I look at this graph, am I right, it's going to be much more expensive? And I said, yes. And then suddenly one side of the table didn't smile anymore. So we have the runoff pattern of risk now. It also explains, I mean, you can now, if we use as risk measure mean square error of prediction, now it explains that the Solvency II MSCP, the 1 year is always beyond the MAC formula or the total formula, and you can now exactly calculate the percentage by which it is below, and you can exactly tell where the difference has to go to, exactly because you know now the runoff pattern for risk. As I mentioned, typically the runoff of risk is underestimated because it goes much slower than the reserves. And legal environment and portfolio characteristics like business line are very important. So, I have spoken a lot about the paper. You can download it from SSRN. We are not going to publish this paper. It will remain there, maybe forever, not forever. But a paper that has colors cannot really be published, and I don't want to argue with publishers about colors. And all these formula, and that's why you should not really worry, all these formulas are implemented already in the chain letter package. This was a coincidence that I met Markus Gessmann just about 1 month before he planned to release the new package. And then I said, stop, still wait, we have now much more. We should also put this into the new version. So all the formulas are already contained in the new R package chain ladder, which can be downloaded from the CRAN website. And now for those of you for which this was much too fast, I'm going to give a workshop jointly with Greg, and this is going to be on May 25th. Now, Greg will give probably 3 sessions, I will give 3 sessions. Now, 2 of my 3 sessions you have already seen. I will do it again, but slower, and I will also explain R code. So for those of you that would like to see the R package and to see how this R code should be used or can be used, please sign up for the workshop. So that's the end, almost. Now it's up to you to ask questions. Thanks.
Thanks, Mario. It's Dimitri. So I'm just, I guess essentially when you talk about the stochastic reserving setting, you're kind of dealing with what you might call probabilistic forecasting. So you're forecasting these distributions and so on. And do you have any thoughts on the some kind of ways to kind of empirically assess the quality of those distributions that have been forecast. I mean, there's some notion of, for example, like calibrated forecaster and so on, and how you might actually go about doing it empirically. Maybe the NAIC data set might be sort of leveraged to some degree. And I mean, going from that, right, if you start thinking about kind of empirical assessment, do you think the kind of empirical quality of predictions could be improved by, I guess, incorporating some additional, I guess, attributes of the claims process and basically exposure details as well as claim details? Do you have any thoughts on whether that's in fact beneficial for this enterprise or how you might go about it?
I mean, that's part of our project. I think one main deficiency of this model is that we assume lots of independence. And I mean, we have other models. There is another paper by Michael and Hashorva and myself where it's not exactly the chain ladder model, but it's a multivariate log normal model. You can either do this in a cross-classified additive way, or you can do it in a multiplicative way. So one is the chain ladder model, and the other one is closer to the over-dispersed Poisson model. And in this multivariate log normal Gaussian case, it's quite easy in mathematical terms, probabilistic terms, to play around with all sorts of correlation structures. And that's exactly what we do in the project, or what I plan to do, and that's where I do some experiments at the moment. But it's quite difficult, because I would say half of the results I see are very unexpected. And especially all these models have lots of problems if there is a trend in one of the three or let's say one of the two directions, either accident year direction or development year direction, and accounting year direction, calendar year direction. So if there is one, let's say if there is a trend in accident year direction, so typically the reserves, they don't remain constant when you increase correlation. And if a second moment influences the first moment, then for sure there is some problem somewhere. But it's not even clear whether a sign goes up or down. I just see that it goes up or down. So I think that's very difficult, but that's what we are working on. And that's probably the main deficiency of these models here, is these strong independence assumptions. And now I have exactly explained what I do in the third session of my workshop.
Okay. Thank you.
No more questions? No? Okay, then I'll close this session. I guess perhaps the thing that is most prominent in the presentation you just saw is that it takes us out of our usual regulatory zone in looking 1 year ahead, or 2 or 3 years ahead, but not to the ultimate situation. So that's unusual for us, but the presentation is none the worse for that, because we shouldn't be always hung up by regulation. We've got companies to run, and in doing that, one is interested in the situation 1 year out and 2 years out. So I found that very refreshing. I remember once when I was being introduced to give a presentation, the person making the introduction said he makes difficult things seem easy, and I've always taken that as the greatest compliment that I've been paid. And I think we saw something of that today. We started with very opaque formulas, and I heard one or two gasps when the first one appeared. But at the end, we saw that those formulas could be understood by children. So one final thank you to Mario.